Yay!
Yay! Okay, here's one more kind of a standard example of circular motion, and this one involves friction. Now we can put that in. And here's the idea. You have, maybe it's a little button on a turntable. Some mass is on a turntable, some distance r away from the center. And what we want to know is, let's just go ahead and put in the mu. Maybe this is static, right? Usually I just call it mu. It's kind of obvious we're not moving. Anyway, the coefficient of static friction is 0.2 between the button and the turntable. And let's say that this r is 50 centimeters away. What we want to know is, what is the maximum RPM that keeps the button still, so that it won't start moving, right? Because you imagine if you spin this thing really, really fast, the button's going to fly off. So we want to keep it there. How is this going to work? All right, so let's draw in our forces. What do we have? This is sort of our standard thing. We have normal force from the turntable and button is that way. mg's headed down that way. One other force that we need to put in is friction. So in problems like this, one of the challenges is to try to figure out what direction is friction operating. So what I do is I try to imagine what would happen to this thing if there was no friction. If there was no friction at all, if this thing were made of ice or something like that, and you started spinning it, what would happen is that this button would start migrating out to the edge. So what friction is actually doing is keeping it in one place, right? So friction is actually acting back that way, to the left, keeping it where it is. So if there were no friction, it would kind of be heading to the right. So friction is actually acting to the left. So here we go. In the x direction, what do we have? We have friction acting to the left, so it gets a minus sign. And I guess that's it, right? I don't see any other forces in the x direction, so we're done. So this is equal to, again, the centripetal acceleration never belongs on the left-hand side, it's on the right-hand side. And what direction is it? It points at the center of the circle, which is negative, so it's minus mv squared over r, right? That's it in the x direction. In the y direction, things are pretty simple. N minus mg equals 0. Okay, so the regular thing happens and it's just mg, no problem. So these minus signs go away. What do we have? The magnitude of the frictional force, we'd said before, is mu times n is equal to mv squared over r. But n is just mg. So this is mu mg is mv squared over r. Now, look at that. It's sort of an interesting thing. I didn't tell you what the mass of the button was, and it turns out it doesn't make any difference. It doesn't make any difference if it's a button or a really heavy box or whatever. The mass cancels. That's kind of cool. All right, so I'm looking for rotation rate, right? So what I'm going to need to solve for first is v. How fast can this thing go? And the v is just going to be, what does it look like? Square root of mu rg. Let's see. That's going to be 0.2. G is what, 10. R is 50 centimeters. That's a half a meter. So it's half of 10. That's 5 times 0.2 is 1. Oh, goodness. So this is 1 meter per second. Neat. And then we just need to use our little trick. We want, if v is 1 meter per second, and I want to go to RPM, what I said was I just divide 10 divided by the r. This is a half. 50 centimeters, half a meter. So that's going to be 20 times 1, or about 20 RPM. So if this thing spins at a rate faster than about 20 RPM, then that button is going to fly off. Neat. So that's, oh, one thing I wanted to mention is the same physics applies in different situations. As long as the free body diagram is the same, we have the same situation. This could be a button on a turntable, no problem. But look, this could also be something else. This could also be another way that you'll see this, maybe in your problem sets in the textbook, is this might also be a car instead of a button. Maybe it's a car trying to round a curve, right? And there's a certain mu between the car tires and the street. And you want to know what the speed is at which the car can negotiate safely without sliding. So you would do it exactly the same way. We get this as a final answer. So this physical situation doesn't have to be button on a turntable. As we'll see as we'll go along, simple diagrams in physics can be used for a variety of really interesting situations. So this could work for a button on a turntable, and it could also be a car rounding a curve on a flat road. Neat. Same physics applies.